So till now we have implemented this activation function, we have implemented dense layer, we have implemented our data loading and also the imports. Now our next step is to implement the softmax and cross-entropy, which is the fifth section of our data, which is cross-entropy. Let's go through it. Now we will create a class softmax cross-entropy. It is beneficial or rather good practice or a simple practice to contain both of this into same class for the case of simplicity. So yeah, we will first implement the forward function here. Forward function will contain the parameter self and then logits and then y. We will be caching y is equals to y. I think this would be fine, and after that exp is equals to, this will save all the exponents, logits minus np dot max logits, and then access and keep dimensions true. So like this exponents is also implemented. Yeah, I'll be explaining this whole part once we write this function. And self dot probabilities will be exp divided by np dot sum, which is sum of, and keep dimensions true. And then we also need to calculate the loss. So loss will be negative of np dot mean and then np dot sum of y times np dot log of self dot probabilities of plus 10 to the power minus 8, which is a very small addition here. After that we will write x is equals to 1 and then return the loss. Now what this does is, this function takes the raw unscaled outputs, which is logits, from the final dense layer. Sorry, I have to write here capital Y. Anything else? Yeah, this one, because our function parameter is capital Y here. And then, yeah, where were we? So I was explaining that this function takes the raw unscaled outputs, which is logits, from the final dense layer, turns them into clean probabilities, and calculates a single penalty score, which is loss, based on the true target labels, which is y. Now what we are doing is we are caching the output here, caching the y here, which means we are saving the true target labels to use during backpropagation. And for the stable exponentiation, uh, we are using this expression. So what this does is, this calculates the exponential of the logits, subtracting the maximum logit value per row, which is a vital trick called numerical stability. And this prevents numbers from getting so large that they break your computer's memory. That means nine errors will not occur if we use like this. And after that, we are computing the softmax probabilities using this expression, which divides each exponentiated value by the sum of all exponentiated values in that row. This normalizes the outputs so that they look like probability distribution. So what this basically means is that the every value will be in the range of 0 to 1, and the row sums up to exactly 1. And after that, we will be calculating cross entropy loss. This measures how close the predicted probabilities match the true one-hot encoded labels. So we have not used one-hot encoded labels here, but internally they have given us the encoded labels. That is why we are saying it. And then we are adding a tiny number which is 10 to the power minus 8 to prevent calculating log of 0. So in a case where this is 0, this will prevent it from hitting the undefined error. After this, we will implement the backward function. So backward function will just take self, then we will calculate m, which is self dot y dot shape, and then return self dot props minus self dot y divided by m. Yeah, divided by m. So what's happening here is this function calculates the gradient of the loss with respect to the input logits, and we are calculating the prediction error here. This is prediction error, and then we are dividing it by m, which is the batch size. So basically we are normalizing it by the batch size. So yeah, this is the implementation of Softmax CrossEntropy. Here also we are using two functions, forward and backward. One is used for prediction pass, which is the forward pass, and other is used for the back propagation purpose.